Let's our discussion of chapter 3 of the textbook, the logic of quantified statement. Let's first give a motivation. The logic we have been talking about in the last chapter, namely chapter 2, is all about statement something like Jim is tall, which only specify the property of a single element. And such logic is called propositional logic. That's the logic we have seen so far. Or statement, or it's called statement logic. Zeroth order logic. However, such a logic has a very limited expressing power. For example, it's not able to express a statement like this: every student registered this course has taken, say, CS 101. Suppose we have such a statement, and also we know Alice registered this course. And we would like to deduce that Alice has taken CS on 1. And this kind of logic is what we are going to learn in this chapter. Another example is, suppose we have a statement like Alice got 100 in quiz 1. And you would like to deduce that there is some student, there is at least, say, at least one student get 100 in quiz 1. And the first one, the statement like this is called universal quantifier, and the second one is called essential quantifier. We are going to, this is what we are going to learn in this chapter. And such logic is called predicate logic. Opposed to propositional logic, or sometimes called quantifier logic, quantification logic, or first order logic. Okay, so let's begin by defining what is a preposition. Sorry, predicate. So a predicate is a sentence that contains a finite number of variables, such that when you plug in certain values for this variable, you get a statement. Remember, a statement is it's called proposition. Is either true or false, but it cannot be both. Okay, let me write this. a predicate is a sentence that contain, the most important thing here is variables. So this the inclusion of variable make it expressing power of predicates much stronger than the proposition logic we discussed previously. Because if you plug in some variable, the predicate may be true, and if you plug in some other variable, the predicate may be false. And they become a statement. I remember a statement is either true or false. Become a statement when specific values substituted. For the variables. Okay, let's move to next page. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. Okay, I think the best way is to give examples. Let me okay, the first one is definition. Let me go back and change this. Say the first one is definition. And the second part, we are going to give some examples. So let me give one variable examples. The first one is px x plus 3 equals 0. Excuse me, and the domain is R. It's very important you specify the domain of your predicate, and as we are going to see very soon. And you can see that for this predicate, I will plug in array x and the predicate is false unless I plug in, I substitute variable with x equals -3. Okay, that means if I substitute x equals -3, the predicate the statement is true. If I plug in x equals -2 and the statement is false, and if I plug in x equals 0, statement is false, and so on. The second one is px x is an FIU student. And in this case, we can have, for example, case one, suppose the domain is the set of all FIU student. And then predicate px is maybe I want to change, maybe to make it less trivial, if I want to change it, I can change to something like x has pencil ID. Okay. In the first case, if D is the set of all FIU students, then px is true for all x in D. And if I change my domain to D equals the set of all people living in Miami, and then px is true for some x in D and false for the rest. And here you can see the power of predicate because it's true and false depends on which value of the variable you substitute, which value you substitute into the variable. Let me give you another example. It's a two-variable predicate. This example is pxy x registered course y. So what is the domain of this? Remember here is the function has two variables. Basically, the domain is a pair. Is a pair of variables. Therefore, the domain is x is a Cartesian product of two sets, x times y. What is x? X is the set of say FIU student, and y can be all courses offered FIU, offered at FIU in the springs, in the spring semester. Or it can be all CS courses. Okay, so this is here we see three examples of a predicate. The next concept I would like to introduce is truth set. Intuitively, it should be very clear that all value x in D such that Px is a true set. So let me repeat again. So all value of x, let me write it down. All values of x in D such that Px is true. As we discussed, for example, in the second example, Px and x has a Panzer ID. This is the true set is just if I'm not wrong, then nobody else outside FIU can have a Panzer ID. That means sorry, that's not wrong. Not correct. The true set is of X has a Panzer ID is, I think it should be all FIU affiliated people. So more formally, the true set of Px is, remember our set definition, X in D, Px. Which is equivalent to say Px equals true. And this is a succinct way of writing Px equals true. We just say Px. Remember, the Px is, when we write Px like this, it means Px is true. Okay, let's move to next page. Let's see example. So let me let's our predicate Pn to be n is a factor of 6. Here, if you don't, if you haven't seen this before, factor means a number divide this number. Okay. So case 1, and why we have to distinguish between two cases, because if your domain is different, and then your answer will be different. The truth set will depend on your domain, as we are going to see. So in the first case, if our domain is D+, then if you remember, recall that the D+ definition of D+ is non-zero integers. That means 0, 1, 2, 3, 4, 5, and so on. So in this case, what is the truth set of Pn is what? Is 1 divided 6, so 2 divided 6, 3 divided 6, and 6 divided itself. However, if I change my domain to integer, just C, then what is the truth set? The truth set will be larger, because -1 also divides 6, -2. So and sometimes we can write it in a more compact way. We just write +-1, +-2, +-3, +-6, which are equivalent. Okay, so our next topic is going to be quantifiers. So a quantifier is just a word specify the size of the truth set. And in particular, we only have two quantifiers. One is called for all quantifier, the other is called the there exists quantifier. And the first one is called a universal quantifier, and the second is called essential quantifier. Okay, so let's go slower. A word, what is a quantifier? Is a word that quantify quantify. Quantify means specify. The size of the truth set. And such as for all, and a symbol is it's this. It's upside down A because for all is any, it's equivalent to any. So for all students registered in this course, they have taken CS 101, and that means any student in this course registered in this course has taken CS 101. Such quantifier is called universal quantifier. And your example is for all x in D, px. The other is there exists. And this is called essential quantifier. We use the notation is a mirrored reversed of letter E, essential. So usually we write there exists x in D such that, I mean, not right abbreviation, such that, and usually we write st for such that px. So let me give examples. Let me give some examples. So suppose that my predicate is px is x squared at least x. So if my domain D is just 1, 2, 3, 4, 5. So what about the statement there exists x in D such that px, it is true or false? Of course it's true, right? Because if you can check, for example, if I plug in x equals 5, then x squared equals 25, of course is at least 5. So this essential quantifier means as long as you can find one element in the domain such that the proposition is true, then you can this statement become true. Okay, and of course this is true. And what about the statement for all x in D as px? And this is turned out to be also true, right? Because if you plot the real axis. So what are the the true set of this predicate is either x at least 1 or is x is less than or equal to 0. So this is a true set. And therefore this statement is also true. So that means for this x in D px, we can either use exponential quantifier, which is true, or I can use universal quantifier, which is also true. By the way, if universal quantifier is true, then automatically the exponential quantifier is true. So if you know every student's, every element in the set satisfy this property, of course, there exists a single element satisfying this property. However, if I change my domain to be real number, and let's see this exists x in D such that px it is true, it's still true, right? Because I can pick any number in this true set. For example, x equals 2, x equals -5, x equals -1, which is also true. And what about this for all x in D px? And this, unfortunately, is false because this is a very stronger statement saying that for every element in X, the statement is true, which is clearly not correct because for element in this area between 0 and 1, the statement is false. The proposition doesn't hold. Okay, let's move to next page. Let's see another example. So there exists X in R such that X bigger than 2 if X is greater than 2, then X squared equals 9. So it is true or false? By the way, this is equivalent to there exists an X in R such that if we use this implied notation we learned from last chapter in the first part of this module, X implies X squared bigger than 9. X squared equals 9. Of course, this is true because this is an exponential quantifier. And you just need to find a single element that can certify this statement to be true. In this case, x equals 3 is the single element. So now we are going to talk about some equivalent forms of this quantifier statement. Equivalent. The first one is for all x in R, x in Z implies x in Q. So what the equivalent form of this? Because R is a superset of Z, and therefore we can simply write for all x in Z, x in Q. And this is our predicate. Okay. The second example is for all x in D, the px implies qx. And similar for this, we can similarly to the previous example, we can write this as for all x in the truth set of px qx. And the third example is there exists x in D such that px and the qx. And which is equivalent to say x in D such that px and qx. Okay, in this case, actually we can, because this is exponential quantifier. So if I say there exists a student in this class, and of course I can say there exists student at FIU, right? You can generalize this. Okay, and the converse is not true. Okay, so you cannot say that there exists. Okay, so if there exists a student in this class, implies there exists a student at FIU, because this class is a subset of FIU. And you cannot say the converse, because if there exists a student at FIU, you cannot say there is a student in this class, something, which is not obviously not true. So my point is, and this is equivalent to say there exists X such that Px and Qx. That means I don't want to specify, I don't need to specify the domain, because the domain can be anything. Okay. So the next topic we are going to talk about is implicit quantification. Quantification. So let's look at what does Px implies Qx mean. If you write a statement Px implies Qx, this means formally, this means for all x in D, Px implies Qx. Okay, so here we use the textbook notation. We use dp for a predicate p. We use dp. Remember, d is used to denote domain of a predicate, and we use dp to denote the truth set of predicate px. Okay. And dq, similarly, truth set of predicate qx. Okay, using the equivalent form we learned just learned before, and this means for all x in dp qx. So what does this mean? And if you think about for a moment, think about this for a moment, this is equivalent to say dp is a subset of dq. Okay, let's move to next page and let's elaborate on this. So so what is for all x px equals q implies qx. So this is px, this is dp. So this statement saying that for anything in this circle, within this circle, it's lie in the circle of dq. It's satisfied because qx means, remember dq is the set of all element making qx to be true, which means qx is the set of point in the set dq. So therefore, px implies qx actually is equivalent to say the true set of predicate p is a subset of true set of predicate q. Okay, the second one is px equivalent to qx. And for the same reasoning, because using the same reasoning we just did before, for px implies qx, and we can easily see that this is equivalent to say dp equals dq. Oh, sorry. Unfortunately, I think I didn't talk about two set are equal, but I think intuitively we have the formula define this. What that mean that two set are equal? But it should intuitively clear what that mean, and that means every element in this set is also element in that set. Also, every element in that set is also element in this set. So this set of two set are equal. Let me finish this video by giving an example. So in this example, we are going to use D is going to be Z++. So let's look at the following three predicate. Qn is n is a factor of 8. Rn is n is a factor of 4. And finally, Sn is n is a factor, oh, sorry. So Sn is going to be n less than 5 and n not equal to 3. So what is the true set of Qn? So dq, you can easily see it's 1, 2, 4, 8. And the true set of dr, the factor of 4 is 1, 2. And what about the true set of S? It's 1, 2, 3, 4. First n less than 5 is 1, 2, 3, 4, and n not equal to 3 is just 1, 2, 4. And from this relation, we can see that Rn implies Qn. Sn implies Qn. Sn and Rn. By the way, sorry, I think I should mention this before. So the notation used in the textbook is if Px and Qx are predicate, with common domain D, then we use this notation Px, this arrow with double line, Qx, to use this for all x, Px implies Qx. And also, we use double arrow to means for all x. Sorry, for double line arrows. For all x, Px is equivalent to Qx. Okay. Because you don't need to look at a statement to deduce this implication relations. You just look at their truth set dq, dr, and ds. Because dr and ds are equal, that means these two statements are equivalent. And because dr and ds are equal and they are both subset of dq, that means whenever you satisfy dr, and you all satisfy automatically dq, that means R implies Q. R implies Q, S implies Q. And therefore we have this relation Rn implies Qn. Sn implies Qn. Rn implies Qn. Sn implies Qn. And finally Sn and Qn are equivalent.